All right, so today we are going to talk about the other type of reasoning, the other way that we can make conclusions, draw new statements, or come up with new conjectures or conclusions based on a different way of thinking called deductive reasoning. Remember, we talked about inductive reasoning. Inductive reasoning is making conjectures or conclusions based on patterns, right? Which is a little bit scary because sometimes those are wrong. We just don't have enough pattern or we make the wrong sort of decisions, right? Deductive reasoning is a little bit more concrete, right? Deductive reasoning is using actual facts, certain statements. So it's a process of showing that certain statements follow logically from agreed upon assumptions and proven facts. So the difference is inductive reasoning is using patterns to make conjectures. Deductive reasoning is using facts. Okay? So for example, we have this graph here. And there are a couple of different conclusions we can draw from this graph. The first one being that the northern elephant seal requires more strokes to surface the deeper it dives. Okay? Now, if we look at that graph, we can see a pattern of the data points trending upward, right? It's in an increasing way. That's what happens when the slope increases, right? It says that as the maximum depth increases, the number of strokes increases. So that tells us that the deeper the seal dives, the more strokes it takes to surface, right? So that's a pattern. We're using a pattern here, so that's going to be your inductive reasoning. Versus a conclusion that a northern elephant seal uses more strokes to surface from 250 meters than from 60 meters. And so now we're talking about actual data points, that one and that one. Those are two facts, right? So this particular seal, needed more strokes when it was 250 meters down to get to the surface than it did if it was 60 meters down, which of course makes sense. But since those are based on proven facts, then we're talking about using deductive reasoning. So that's the difference. Facts or pattern. And we'll use that here as well, right? Tell whether the statements are deductive or inductive reasoning. Angela knows that Walt is taller than Peter. She also knows that Peter is taller than Natalie. So Angela reasons that Walt is taller than Natalie. Is that deductive or inductive? Well, it's not a pattern. She knows these things. She knows that Walt is taller than Peter. She knows that Peter is taller than Natalie. So she, of course, makes the decision that Walt is taller than Natalie. That's deductive reasoning. She's using known facts, right? Versus number 2, Josh knows that brand X computers cost less than brand Y computers. All other brands that Josh knows of cost less than brand X. That Josh knows of. So Josh reasons that brand Y costs more than all other brands. The problem is he hasn't looked at all other brands, right? So he's basing this off of a pattern that he's established, and so this is your inductive reasoning, right? Think about number 3. For the past 3 Wednesdays, the cafeteria has served macaroni and cheese for lunch. Dana then concludes that the cafeteria will serve macaroni and cheese for lunch this Wednesday. What do you think, deductive or inductive reasoning? It's going to be inductive reasoning, right? She's making that decision based off of a pattern. Now, deductive reasoning would be if she had the actual menu in front of her, the schedule for the menu in front of her, and it said that macaroni and cheese was going to be on Wednesday. Then she'd be using deductive reasoning, all right? 4, if you live in Nevada and are between the ages of 16 and 18, then you must take driver's education to get your license. Anthony lives in Nevada, he's 16 years old, and has a driver's license. Therefore, we conclude that Anthony took driver's education. Deductive or inductive? Well, this is all based on facts. So, of course, this is going to be using deductive reasoning. Okay? All right. Moving on. When you're using deductive reasoning, there are a couple of laws, a couple of structures to our conclusions that might help us identify if a conclusion is possible or if it's reasonable or not, right? And one of those laws is called the law of detachment. And what that says is, if you have a condition, a conditional statement, if you have a hypothesis and a conclusion, if you have a condition that if it's met, then this particular conclusion will happen. Then, if that's true, then all you need now is for the condition to take place. So what it says is if the hypothesis of a true conditional statement happens or takes place, is what I want to change this to, then the conclusion is going to be true. For example, if we know that Mary goes to the movies every Friday and Saturday night. Tonight is Friday night, right? Or today is Friday. Then if that's the case, the condition is that it's Friday or Saturday night. And the conclusion would be that Mary goes to the movies. So since today is Friday, we can assume that Mary will go to the movies. And that is your law of detachment. Okay? The law of syllogism is a different way of thinking, a different way of attaching some different ideas. The law of syllogism is kind of what we used in that height example a second ago with Walt and Natalie and everybody. It basically says this: if you have an if-then statement, that is true. So if a particular hypothesis happens, and then a conclusion is going to happen, right? Then you have a second if-then statement that uses the first's conclusion as its hypothesis. Then what you can do is you can cut out the middleman and start with the hypothesis of the first if-then and go right to the conclusion of the second if-then, right? And it's a way of linking two seemingly unrelated items sometimes, right? So we introduce these variables P, Q, and R with the intent of trying to make this a little bit more robotic and a little bit more mechanical, right? Here's what I mean, right? We have an if-then statement. Then we need P to go to Q, right? So P leads to Q in the first statement. Well, the second statement then has to be that Q leads to R. This statement and this statement need to be the exact same. That's the only way law of syllogism works. It's the only way to guarantee that when you write P going to R, which is what you would do here, that's going to be true, right? So the Q has to be linked. One of the conclusions of an if-then has to be the hypothesis of another one. And if that's true, then you can link the hypothesis and conclusions of those two, right? It's a little bit confusing to try to say, but that's basically it. Okay? So let's try to use it, if possible. Let's talk about when law of syllogism might hold up and when it might break down. So here, if Rick takes chemistry this year, then Jesse will be Rick's lab partner. If Jesse is Rick's lab partner, then Rick will get an A in chemistry. And we're going to assume that these two statements are true. Right? Here's what we got. Here's the first if-then, and we can make this P. Rick taking chemistry this year is going to be P. Jesse, being Rick's lab partner, is going to be Q. So far we have P going to Q. That means that the next if-then needs to have the Q as its hypothesis, right? So Jesse will be Rick's lab partner is the hypothesis of the next statement. So we do have Q, but now Q is leading to a different conclusion, which is Rick will get an A. So that's Q leading to R. So what that means we can do is we can take P and jump straight to R and say, if Rick takes chemistry this year, then Rick will get an A in chemistry. Okay, the conclusion of the first statement is the hypothesis of the second statement. So then we can do this. We can jump straight from P to R. Okay, so that's where it holds up. This one says, if a polygon is regular, so here's a P, then all angles in the interior of the polygon are congruent. This is Q. So this is P leading to Q. that means that Q needs to be a hypothesis of the next if-then. But if you look in this next if-then, it says if a polygon is regular. It's the same as the first. So it's P again. This does not follow the law of syllogism, since these are not the same. So we're not going to be able to use the law of syllogism to write a new statement. It's just not possible. Okay? So that's your law of detachment, law of syllogism, and in deductive reasoning where we're using facts, which is what we're going to use most of the time when we're writing our proofs. We'll talk more about that when we get to our proofs. Okay? All right. Next, postulates and diagrams. We want to talk about some of these postulates, right? We've talked about two postulates already. Postulates, the segment addition postulate, the angle addition postulate. These are two things that seem to be quite obvious, and postulates should, right? Because postulates are geometric rules, and there's lots of different types of geometric rules. Postulates, theorems, and then there'll even be corollaries thrown in there some. But postulates are rules that we just accept as being true. If you want to think of it this way, it's kind of the conjectures that we get from inductive reasoning very often, right? We don't have proof of every possible situation, but we're making these decisions based on a pattern, right? And so we just accept them to be true until someone comes up with a counterexample, all right? Now, we'll use those postulates to help us come up and prove theorems. Theorems are going to be a little bit more advanced. So postulates, because of its nature, should be incredibly obvious, but we need to acknowledge them and be able to recognize them and be able to tell when the postulates hold up and are true so that we can use them to prove theorems. Theorems are going to be a little less obvious, so therefore probably a little bit more interesting in terms of what they'll allow us to do. Okay? So, some of our postulates. The first postulate says, through any 2 points, there exists exactly one line, right? So we talked about that before. It takes 2 points to name a line. It takes 2 points to graph a line. But basically, this is saying that if you have 2 points, then there will be exactly one line that goes through those 2 points, okay? The next postulate says what sounds to be the same, but it's sort of in reverse. A line contains at least 2 points. Right? You can't have a line that contains only 1 point. That doesn't make sense. So you need to have at least 2 points. And we already talked about how lines have quite a few more than even 2 points. The next postulate, if 2 lines intersect, then their intersection is exactly 1 point. And we went around the room and modeled some things in the room with points, lines, and planes. Some of you guys were able to point out the fact already in that particular instance that when 2 lines intersected, they intersected at a point. Well, they intersect at exactly 1 point. They're not going to touch in more than 1 point. Okay? This next postulate, and if you notice, I haven't really been listing the numbers of these postulates. That's because the numbers are kind of arbitrary. I don't need you to memorize the numbers. If you can just remember what they say, right, and paraphrase what they say, you're better off, because these numbers can change based on the textbook that you use. All right, but anyway, the next postulate says through any, now we're going to move to planes. Through any 3 non-collinear points, there exists exactly 1 plane. Okay, so if you have 3 non-collinear points, then there will be exactly 1 plane that those guys will sit in. We've talked about that a lot as well. It can go the other way now, and you can talk about, okay, and it's all about what you know first and then what you get to conclude. So this says a plane contains at least 3 non-collinear points. So if you have a plane, then you know that it will have at least 3 non-collinear points in it. Okay? The next postulate says that if 2 points lie in a plane, then the line containing them lies in the plane. And that sounds pretty obvious, right? But basically it says, all right, if we've got 2 points in a plane, then we know that there's a line that will be in that plane as well. It contains those 2 points. Okay? And then this last one here, again, it talks about the intersection. An intersection of two planes. If you look at the two walls in your room right now, two walls that come together in that corner can be a line. So two planes intersect, and their intersection is a line. Okay? So it's really about what you know and then what you can conclude, right? So identify a postulate illustrated by this diagram. So what's going on in this diagram, right? Well, you've got if, and you've got two lines intersecting. So if two lines intersect, then they intersect at exactly 1 point. And so that's postulate 7, but whatever. If two lines intersect, then their intersection is exactly 1 point, is being illustrated by that first diagram. Diagram B. Okay, if two planes intersect, then we know that they're going to intersect at one line, right? So if two planes intersect, then their intersection is a line. Okay? All right. So using the idea of what do we have, what can we conclude? So in this guy, if there are three non-collinear points, then we know that there is a plane. This is the conclusion we'd make. There is a plane that contains those 3 points. So this is postulate whatever, I don't know what number, but through any three non-collinear points, there exists exactly one plane. Okay? And we'll keep trying to use diagrams to pull some of these postulates out and put them to use, get them out of theory and put them to use, right? So use the diagram to the right to help write examples of the postulate. Here's what we mean, right? So postulate 9, whatever. Postulate 9 says that a plane contains at least three non-collinear points. An example of that from here would be that plane, what? Pick any plane. Plane Q, right? So what you would want to write, instead of writing all of this, you would just write that plane Q contains what? V, Y, and W, right? That's it. Plane Q contains V, Y, W. So if you have a plane, then there are three non-collinear points in that plane, right? The next postulate, if 2 points lie in a plane, then the line containing them lies in the plane, right? So the diagram, from the diagram, can you find an example of that? And I'll get rid of this now. That's the postulate. But what you could say is, well, if 2 points lie in a plane, find me 2 points in a plane. Any 2 points. Okay, and I know that there are multiple points you could use. We could say maybe VW, right? So if VW, V and W lie in Q, which they do, then line VW lies in Q. Would be something that you could write as an example, right? And then postulate 11 is the one that says the intersection of two planes is a line. So pick that out of this particular diagram. You could say plane Q, excuse me, and plane P intersect at B, because that's the intersection of those two planes. Okay? All right. Modeling. Let's continue to do this. Let's model two more, right? Postulate 9, which says, I've already forgotten, postulate 9, which says a plane contains at least three non-collinear points. So in this diagram, can you pick that out? One way you could do that is to say that plane P contains at least the points A, B, and C. So plane P being here, containing at least A, B, and C. Okay? Postulate 10, which says 2 points lie in a plane, the line containing them lies in the plane, right? Then, using this diagram, you could say, what? that point A and B lie in P. Therefore, line N is in plane P as well, right? Using that diagram. Okay? All right. It also gets us to a place where we need to be able to sketch diagrams from information, right? We talked about this a little bit as well. We tried this before. So this says sketch a diagram showing line TV intersecting segment PQ at point W so that segment TW and segment WV are congruent. So be careful. All right, let's see. To sketch this, right? Pretty easy. First thing we want to do is sketch segment PQ. Right? And then we need to sketch line TV. Now notice that line TV is not bisecting PQ. Those aren't the two segments that we have congruent. So you can really draw this wherever you wanted. And I'm going to move this down to give me more room. Right? But we could do this. T and V. But when we do that, we need to understand that TW, and it intersects at W, so include W. And now we know that TW and WV are congruent, so those two segments are congruent. You'd want to mark those guys congruent, okay? But sketching from the diagram all the information that we can possibly put in there. We want to do that, okay? All right. Next, which of the following statements cannot be assumed from the diagram? Take a look and see if you can't figure out which one that is. Stop the video for a second and then check it out. Okay? A, B, and F are collinear. Well, here's A, here's B, here's F. Can we assume that those guys are collinear? Yeah, that's true, because they're sitting on the same line. Right? What about E, B, and D being collinear? E is here, B is here, D is here. Okay, they're not currently being shown that they're on the line, so we can't assume that. Right? So this is false. We can't assume that right now. Right? How about segment AB being perpendicular to plane S? Segment AB is right here. And is it perpendicular to S? Right? Remember, perpendicular lines, we've seen this already. It form a right angle. So hopefully you remember that from years past. Well, there is a right angle box right here. So, and it's formed by AB hitting that plane S. So yeah, we can assume this. Right? We've talked about before also not assuming too much from a picture. You have to go with what you know and what you can prove and that kind of thing, the information you're given. What about segment CD being perpendicular to plane T? Well, here's CD. Can we just assume that it's perpendicular to T? There's no right angle box. So no, we can't assume that. We'd have to have that right angle box. Okay, what about line AF intersecting line BC at point B? Can we assume that? Can we assume that AF and BC intersect at B? Yeah. Yeah, that's exactly where they intersect. So that's going to be true as well. Okay? All right, so there's your postulates, your beginning foundations of the arguments that we're going to make later. And your deductive reasoning. So homework's out in Canvas. Give that a shot. We'll talk about it next time.